Okay, so this is our final video in our functions and graphs topic, and we've now introduced a whole lot of new graph shapes, the hyperbola, the truncus, the exponential graph, graphs of circles and graphs of semicircles, and we've talked throughout the topic about applying transformations to those basic graph shapes in order to sketch variations of those graphs. The final thing we want to look at here is calculating intersections between graphs. Okay, so coordinates of points of intersection between two different graphs, for example. So we have to remember that when we looked at simultaneous equations right back in term 1, we recall that the coordinates of the points of intersection between two graphs can be found by solving those equations simultaneously. And when we solve simultaneous linear equations, we have two algebraic methods available to us: substitution and elimination. Now, elimination works nicely when it's two linear equations, certainly in particular situations, and that's because, and the aim there is to eliminate a variable. Elimination doesn't work so well when you have two different kinds of equations. They're not both linear, for example. So generally speaking, when we're dealing with intersections between graphs, substitution would be the better choice. Also, usually when we're dealing with intersections between graphs, the two equations are given as y equals something. And we know that substitution is always the best method whenever at least one of the equations is x equals or y equals something. Substitution is the immediate thing that we would jump to then. So generally substitution is going to be the best way to go here. Okay, so let's just work through some examples. So we want to find the coordinates of the point or points of intersection between the graphs with the equations y equals x, x squared plus y squared equals 4 and y equals 2x. Now, thinking about what we know about graphs, x squared plus y squared plus equals 4 is a circle with its center at the origin and a radius of 2. Okay. So if we just think a bit about what we're expecting, it doesn't ask us to sketch a graph, but I always think it's helpful. You don't have to draw it necessarily, but thinking through in your mind, what is happening here? What does it look like? Therefore, what am I expecting about my answers? So we've got our circle with a radius of 2, and we've also got y equals 2x, which is a straight line with a gradient of 2. Okay, and so I would expect that when we solve these equations algebraically, we're going to find 2 points of intersection. There's also probably going to be some symmetry about the coordinates of those points. So for example, if this point up here, was AB, then this one is going to be negative A, negative B. So we're certainly going to get some symmetry happening there. So does my answer make sense? Should be kicking in as well. Okay, so we're going to substitute. So if we think about this as being equation 1 and this as being equation 2, we're going to substitute equation 2 into equation 1. And that is y is equal to 2x. Let's put that in place of y. Okay? So therefore we're going to have x squared plus, in place of y, we're going to put 2x squared equals 4. Okay? So we substituted y equals 2x into the first equation. And now we want to focus on solving this equation. So the brackets around the 2x really matter, because remember, 2x squared is not the same as 2x all squared. So it is 2x all squared that we mean here, and 2x all squared is 4x squared equals 4. So x squared plus 4x squared, well, that's 5x squared equals 4. And divide both sides by 5, so we get x squared equals 4/5, and therefore x is plus or minus the square root of 4/5. Sorry, I just thought I'd mistyped something there, which is root 4 is 2, so that's plus or minus 2 on root 5. Or if we were to rationalise the denominator there, multiplying the top and the bottom by root 5, that would be plus or minus 2 root 5 on 5. Either of these is fine. You don't have to rationalise the denominator. Okay, so what we found there, that's the x coordinates of the 2 points. So we've now found that, this is 2 on root 5, and this one is negative 2 on root 5. So we want to find the y coordinates of the points. So we're going to need to substitute back into either equation 1 or equation 2. Now, if I've got the choice between going back into the circle or into the linear equation is a much nicer equation. Okay, so we know when x is equal to 2 on root 5, y is going to be equal to 2 times x, so 2 times 2 on root 5, So that is 4 on root 5. And we know when x is equal to negative 2 on root 5, y is equal to 2 times negative 2 on root 5. And so that is, sorry, that's a bit illegible. And so that is going to be negative 4 on root 5. And so therefore, our 2 points of intersection between the circle and the line are 2 on root 5, 4 on root 5, or negative 2 on root 5, negative 4 on root 5. And again, you can rationalise those denominators, so they'd be 2 root 5 on 5 and 4 root 5 on 5 if you prefer. Okay. Alright, example 2. Now I've realised that there's actually an error in the question here, so I'm going to use my CAS here, even though it doesn't instruct me to, because we don't actually have the tools to solve one of these equations yet, but we'll get to that in our next topic. So example 2, we want to find the coordinates of the point or points of intersection between the graphs of y equals 2 to the power of x plus 3 and y equals 32 versus y equals 3. Okay, so let's perhaps just have a quick think about what we're looking at here. So this is an exponential graph, no reflections, so it's going to be this shape. It has gone to the left by 3 though, but that's not going to have a huge effect on how we sort of draw our rough sketch. So left by 3, left by 3. We're essentially going to have some sort of exponential graph though. When x equals 0, y is 2 to the power of 3, so y is 8. Okay, so this might be, say for example, 0, 8. So that's the graph of y equals 2 times x plus 3. And if I want to know where does that intersect with the line y equals 32, well, y equals 32 is a horizontal line with y coordinates of 32. Okay, so therefore in part A, we're going to be trying to find the coordinates of this point here. In part B, we're looking at where does this exponential graph intersect with the line y equals 3. Well, y equals 3 is going to be down here because it's got to be less than 8. My scale's not perfect there. That's okay. So we're going to expect, just thinking about what we know, so this is going to be our answer to part B, this is going to be our answer to part A. We're going to expect to have a negative x coordinate in part B, whereas we expect a positive x coordinate in part A. Okay, I'm just going to make that graph a bit smaller, just so I can, I've got some more room, might just pop it over here as well. Okay, so let's think about y equals 32. So again, substitution, okay, if we're going to substitute y equals 32 into our other equation so we can solve it, we're going to get 32 equals 2 to the power of x plus 3. So part A is going to be 32 equals 2 to the power of x plus 3. Now, casting your mind back to our index laws topic back in semester 1, solving an exponential equation, our first aim is to see if we can solve the equation by writing both sides with the same base. Now 32, I know 32 is 2 to the power of 5, and that's equal to 2 to the power of x plus 3, and so therefore the only way that those two things are equal is if 5 is equal to x plus 3. So by writing both sides with the same base, we can then equate the powers. And now we know 5 is equal to x plus 3, taking away 3 from both sides, x has to equal 2. Now remember we want the coordinates of the points of intersection, so the x coordinate is 2. Now the y coordinate, now we could substitute 2 back into our exponential equation, but hey look, y is equal to 32. We've just found when y is equal to 32, what does x equal? And so therefore the point of intersection is 232. Okay, with part B, we're looking to let y equal 3. So that means we need to let y equal 3 in the exponential equation. So 3 equals 2 to the power of x plus 3. Now the problem we have here is that the tools that we've used so far are not available to us. If we want to solve this equation, our exponential equation, we want to try and write both sides with the same as powers with the same base. 3 is not a power of 2. And so therefore we cannot solve this using this method. We actually need logarithms, which is what our next topic is, and so once we get a bit into our next topic, you'll be in a position to be able to solve this equation by hand, but currently I can't solve it by hand, so I'm going to for now solve it with my CAS. And so I'm going to give these to 2 decimal places where necessary. Okay. So I'm going to solve 3 equals 2 to the power of x plus 3. I'm going to solve that for x, comma x, and I'm going to press Control Enter to get a decimal value. Okay, so we see that x is approximately, now I've said 2 decimal places, approximately equal to, now the question would need to tell you how to round it, but as I said, this is an error on my part. I think we reordered the course slightly and I missed that we would need our logarithms here, which we haven't yet covered. So x is equal to negative 1.42, and again, we don't need to sub that in to find the y coordinate because we already know this is the value of x when y is equal to 3, and so therefore the coordinates of the point are negative 1.423. And again, that matches with what we sort of predicted by thinking through graphically what's happening. Okay, example 3. Find the coordinates of the point or points where y equals 1 on x intersects with y equals 2x plus 1. Okay, so again, let's have a little bit of a think about. We know y equals 1 on x, well that's a hyperbola. No translations, no dilations, so that's going to look something like this. And then y equals 2x plus 1 is a straight line with a gradient of 2 and a y-intercept at 1. Okay, so we've got y equals 2x plus 1, and we've got y equals 1 on x, and we want to find where they intersect. Okay, so we can substitute one into the other. If 2x plus 1 is the same as y, we can put that into our other equation so that we have a single equation. So what I'm saying here is this is equation 2, this is equation 1. I'm substituting equation 2 into equation 1. That is, I'm putting, in place of y, I'm going to put 2x plus 1. So that is equal to y. I'm going to put that in place of y over here. So we're now going to have 2x plus 1 is equal to 1 on x. Solving that equation is going to give us the x coordinates of the points of intersection. Okay, so first thing I don't like about any equation is when there's fractions involved. So I'm going to get rid of the fractions here by multiplying everything in this equation by x. So therefore we're going to get 2x squared plus x equals 1. And now we can see actually it's a quadratic. 2x squared plus x minus 1 equals 0. And again, this is why your quadratic skills don't go away. Okay, so it's a harder or non-monic quadratic. So I'm going to do 2 times negative 1 to give me negative 2. And I'm looking for factors of negative 2 that add up to positive 1. That's going to be positive 2 and negative 1. So I'm going to rewrite the middle term. So I have 2x squared plus 2x minus 1x. You don't have to use this method for factorisation. I advocate this because it works all the time, but I'll admit the numbers here are much easier because everything's a prime number, 2's and 1's. So some of you will be able to factorise this efficiently just by sort of trial and error and working with the numbers. So I'm going to continue with this method though. Factorising the first two terms, common factors there are 2x, leaves me with x plus 1. Common factors in the second two terms, negative 1, leaves me with x plus 1. And so taking out x plus 1 as my common factor, I get x plus 1 times 2x minus 1 equals 0. X plus 1 equals 0, so x equals negative 1. Or 2x minus 1 equals 0, so x equals 1/2 using our null factor law. Okay, so we've got the x coordinates at our 2 points. Okay, so what we've now found is the x coordinate of this point is negative 1, and the x coordinate of this point is positive 1/2. And so now we need to find the y coordinates. Now you can substitute back into either of your original equations, whichever one you prefer. Okay, I might sub them into the linear equation, it's generally easier. We're going to sub into equation 2. Okay, so we're going to see when x equals negative 1, y is going to be 2 times negative 1 plus 1. So that's negative 2 plus 1, which is negative 1. And, when x equals positive 1/2, y is going to be 2 times 1/2 plus 1. 2 times 1/2 is 1, 1 plus 1 is 2. So therefore, our coordinates are going to be negative 1, negative 1, or 1/2, 2. Okay, so again, having a quick look at our graph over here, so we've found that it's negative 1, negative 1, and 1/2, 2. So obviously I haven't drawn a beautifully to scale graph, but we've got a bit of a sense of what's happening there. And our answer certainly makes sense given the diagram we drew. Okay, let's have a look at, I think, one last example. Sorry, my screen's a bit glitchy. Okay, find the coordinates of the point or points where x plus 2 all squared plus y minus 1 all squared equals 6 intersects with y equals x plus 1. Okay, so this is a circle. Equation 1 here is a circle with a centre at, what have we got there? Negative 2, 1, and a radius of root 6. Now root 6 is definitely bigger than 2 because root 4 is 2 and root 9 is 3. So it's somewhere between 2 and 3. It's a radius of somewhere between 2 and 3. And we want to see where that intersects with x plus 1. So just a bit of a rough sketch, just to give me a sense of what's happening here. Let's have a think about it. In fact, I might just draw it over here, given that I've got that box in the way. So negative 2, 1. Right, so let's say that's negative 2, 1 there. We know the radius is going to be somewhere between 2 and 3, so that means it's going to go a bit past, given that that distance is 2, it's going to go a bit past there. So sort of, roughly plotting out some points, we're going to have a circle that does this. And then we've got the line y equals x plus 1. X plus 1 has a gradient of 1 and a y-intercept at 1. And so we are going to be intersecting once there looks like a fairly small positive number, and once there looks like it should be to the left of negative 2. Just as a rough guide of does my answer make sense. Okay, so substitution generally the best option. It's always easier to substitute the simpler equation into the harder equation. So the simpler equation, the linear equation, tells me that y equals x plus 1. Let's replace y in the other equation with x plus 1. Okay, so we're going to substitute 2 into 1, and we're going to get x plus 2 all squared plus, sorry, not y is x plus 1, x plus 1 all squared equals 6. Okay, so we've substituted for y, there's the y there, and now we want to solve for x, so let's work on this equation. I'm not going to expand that out. Oh, yes, I am, because I'm going to have another x squared here. So we've got some x terms to collect together. So expanding out the first perfect square, x plus 2 all squared is not x squared plus 4, in case you were tempted. It's x squared plus 4x plus 4. Remember, expanding out your perfect squares, a plus b all squared is a squared plus 2ab plus b squared. Inside this bracket, we've got x plus 1 minus 1, so that's just x. So it's just x squared there. And that's going to equal 6. Okay, so we've got 2x squared plus 4x. Let's take away 6 as well, so minus 2 equals 0. Nice common factor of 2. X squared plus 2x minus 1 equals 0. Factors of negative 1 that add up to positive 2. Okay, they don't exist, so what do we do if our quadratic doesn't factorise? Yes, we can complete the square. Personally, I never use completing the square for solving, because that's what the quadratic formula is. So, quadratic formula, negative b plus or minus square root of b squared minus 4 times a, which is 1, and times c, which is minus 1, over 2a. So again, quadratics coming back to haunt. Negative 2 plus or minus, so what do we got here? That's going to be 4 plus 4 over 2. So negative 2 plus or minus root 8 over 2. And so root 8 is 2 root 2. And then dividing everything by 2, we've got negative 1 plus or minus root 2. Okay, so then we want the y values. Okay, so the y values, always easier to go back into the linear equation. Okay, so we're going to substitute into equation 2. And so we know when x is negative 1 plus root 2, y is going to be, so what's the equation again? X plus 1. So y is going to be that, plus 1. And look, that negative 1 plus 1, they cancel out, so y is just root 2. And we also know when x is negative 1 minus root 2, y is going to be negative 1 minus root 2 plus 1. So what I'm using here is that the equation is y equals x plus 1, so I'm substituting the x value in place of x to work out what the y value is, okay? And when we do that, sorry, I lost that 1 in there, just be careful about that. Negative 1 minus root 2 plus 1, so again the negative 1 and plus 1 cancel out, and here we just got minus root 2. So therefore the coordinates of the points, when x is negative 1 plus root 2, y is root 2, and when x is negative 1 minus root 2, y is negative root 2. And again, that's fitting with what we're seeing. This is clearly a negative number, this is going to be a positive number because root 2 is bigger than 1. So this is a positive and a positive, this is a negative and a negative, okay? And that makes sense given where we were expecting the points of intersection to be. a positive and a positive up here, so that's going to be the -1 plus root 2, and a negative and a negative here, so it's going to be -1 minus root 2, root 2. Okay, and so there is our coordinates of our points of intersection. So there's a mixture of work to do here across a number of topics because I've saved up all the points of intersection questions to do them all at once rather than do them as we did each of the separate function types. So some from exercise 7i, 3j, which will be the exponentials. I want you to try, I'll check the questions, but if any of the ones in 3j you can't write both sides of the equation with the same denominator, with the same base of an exponent, like what we saw in part B up above, you can use your CAS then, but I want you to try your best to solve all of these by hand. It might just be a slight error on my part. There was also an error, I edited most of this, but I missed the exercise 7j. So exercise 7j, the page number listed there in your booklet isn't quite correct, and the question should be 13AB, not 16AB. Okay, so can you just make sure that you're doing the right questions when you do that exercise? Okay, but that is your work for today.